Good afternoon, everyone. Good evening and good morning. My name is Isabel from the video marketing team, and I want to welcome you to this new webinar. If it's your first time in one of our webinars, first of all, welcome to the VDA metal cutting community. And if you are a returning, let's say, webinar participant, thank you very much for returning again today. Today, we are going to speak about indexable drilling. It's one of the topics that was really requested by you, and we always listen to your suggestions. Our presenter, Vladimir, is a very experienced training expert. He's done all kinds of trainings from basic to advanced metal cutting courses, and he has 16 years of experience in the industry. So he's the perfect presenter. Today is going to show you all the basics of indexable drilling, show you some video examples, tips and tricks, and also a very nice comparison between indexable drills, modular drills, solid drills, and so on. But before we start, a few words of safety. As you know, this is one of the core values at VDA. We want to make sure that you are all in a safe environment, checking your surroundings. If also you are in the office or somewhere else, checking the emergency exits. And obviously, if you are driving, we recommend you stop because we are going to show a presentation, and you know, that is really part of the webinar. And if you manage to see the presentation, it will be much better. Obviously, we are happy to get your questions, so feel free to write your questions in the questions panel. It's on the right of your screen. You will see questions. Please write your questions there, and at the end of the webinar, we will dedicate 15 minutes to the Q&A session. And we are also going to send you a survey after the webinar, so make sure that you answer the questions in the survey, because that really helps us for the next webinars to improve our current one, and in general to get new ideas from you. So I will leave you to the presentation. Vladimir, hope I didn't forget anything, and enjoy the webinar. We will be here for you. If you need anything, just write it in the questions.
Okay, thank you, Isabel. Hello, everyone, ladies and gentlemen. Let me introduce today's topic of today's webinar. It's indexable drilling. It's one of the most important operations and applications in the workshop. Today, during this hour, we will talk on several subtopics, if I can put it so. It will be concerning basics, and not only basics, some advanced things. Also, during the webinar, there will be some questions to you, so be ready to shortly answer. There will be all very easy questions, and there will be some videos from practice about the topic, about the elements of the webinar we will discuss today. So, shortly about the content what will be showed now during this 40, 45, or maybe 1 hour. Types of the drills overview, because we will compare different types of the drill, but basically we will be concentrating on indexable ones, because I want you to learn more about advantages of indexable drills, why to understand better why it's so important and why it's so widely used in a lot of workshops. What tips and tricks we can learn and use in a workshop to operate with indexable drills better. Also, we will have a troubleshooting sessions. And also, very shortly, we will touch the topic about cutting forces and cutting data. And also, we will learn some formulas, and we will finish with economics of drills. So where is the advantage of indexable drills there? So what's about when we are choosing the tool, the drilling tool, for example, indexable one, so indexable with indexable inserts, first of all, we need to consider different parameters of the hole. For example, hole configuration, because hole can be blind, can be through, can be stepped, can be flat with flat bottom, can be half. For example, when you make a plunging operation to make a half hole, a half diameter hole, and can be also cross hole. I mean, build through the another hole which is been machined before, and so on and so on. With the countersinks, with chamfers, with another elements. And depending on that, we are choosing the drilling tool, not first of all, but it's one of the most important parameters we need to think about. And next is the size of the hole, for sure, which hole we need to machine, and that will guide us which type of drill we need to choose. A small diameter, 2 mm, below 2 mm, 20 mm, 200 millimeters, and so on. And the length, the depth of the hole, is it 1 diameter, 2 diameters, 8 diameters, 70 diameters, and so on. Also, each hole on the drawing has its tolerances, and also we are producing these holes of different materials like steel, composite materials, cast irons, aluminum, titanium, hardened steels, and so on. Tolerances also can be wide, can be very, very narrow. There can be special demands about straightness, positioning, and so on, roughness. But also, this is just a parameter of the hole. But after we want to produce the hole, we sometimes have a choice which drill to choose. One drill, one design of the drill, another design of the drill, third design of the drill with the same dimensions. And we need to understand which drill, what each drill will bring to you. What productivity at first, what the time per hole it can provide to you and to the workshop, and first of all, what the tool life approximately, at least comparison of tool life of different drills to machine this hole. Another parameter also important, it's cost per tool or expenses on tool after you will start to use them. So basically the most important, it's price per carbide, also the most widely used cutting tool material in the world, and for productive metal cutting, it's one of the most expensive materials. So the tool per cost, I mean mostly the cost of carbide is being used in the tool. But much more important than the previous parameter, than the cost, is the cost per component, per part of your hole. So if you have a mass production, but not only mass production, so middle series production and so on, it's much more important to understand how much time you will spend for the batch of holes, for the batch of components, and how many dollars or euros it will cost to you. And in most of cases, the price for the tool is not that important, so it can be much higher than another type of tool, but it can bring much lower cost per hole. For sure, we can produce holes with different ways. Most obvious for you, it's drilling, but for sure we can use also a milling cutter for them. For example, by helical interpolation, we can produce the hole depending on the configuration of the hole, depending on the conditions inside the machine tool, and so on. Also, we can use boring tools, reamers, internal turning tools, and also taps. But taps, for sure, it's not like producing a hole. It's like producing a thread inside the hole. So last ones are not pure hole making tools. They are hole finishing. So basically, it's not possible to produce by reamer or by current turning tool the complete hole in most of cases. And if to compare drilling versus milling, for sure, in most of cases, milling is most productive because it's producing the hole on one shot. So, time we'll spend for the whole here will be minimal. And let's talk closer to the topic. So to the drills, which drill to choose? For sure, we can think about solid carbide drills or solid HSS drills, but we will not touch these tools today because it's not productive at all because of the cutting material. Also, we can use modular drills, so with exchangeable cutting heads, and indexable drills. So what is the difference between them in usage? But before we will come up to the answer to this question, I want to ask you to just to vote in the poll, which will now appear on the screen. So just for our information, so we want to learn from the auditory who is using which type of drills more frequently. So you can vote for several variants. Solid carbide drills, modular drills, another drills, HSS, for example, with big diameter or small diameter, indexable drills, or other special types of drills. For example, gun drills, deep hole drills with wiring pads, with carbide pads. Unfortunately, I have another. I cannot add another variants because basically we have much more. But here in this poll, we have only 5 variants to choose. Oh, it's very interesting results. So about 1/3 for indexable, 1/3 for modular, and 1/3, a little bit more now, for solid carbide drills. Very well, thank you very much. I will show now the poll. So I see that you are still voting for your variant. Okay. So now you can see that, yeah, the solid carbide drills won this competition, if I can put it so. But yeah, today's topic is about indexable drills, and we will touch solid carbides too, but only properties of other drills like a solid carbide versus indexable. So, one second. I hope you can see now the camera, so you can see me and some tools here I was operating with from time to time. If you cannot see the camera, please let me know, because now the camera session will be. So, indexable drilling. So here, if you see now the camera, we have the indexable drill. So it consists of metal or steel body coated, which coating is provide protection against abrasive wear and against chemical wear. And also you can see here the drill has the full length, the length of the cutting or working part. It has a shank, ground shank, according to ISO 9766. And also it can be different. There can be different shanks, modular shanks, KM shanks, HSK shanks, and so on. It has internal coolant channels, which are starting here from the one big hole in the center on the back of the drill. It has also chip flutes, so they are designed to evacuate chips. And let's look a little bit closer to the drill, to the top of the drill. So now, okay, one second. Here's the top of the indexable drill. So you can see here there are main players or main elements of the drill. So peripheral insert, carbide usually, and central inserts. So main task for them to overlap or to cover whole radius and during the rotation, the whole diameter of the drill. So basically you can see these drills are looking like drills with two cutting edges with two teeth, but in reality it's one tooth. So, and these inserts are put on different positions, and between them there is edges because of the different reasons, because of the production inserts reason, because of the to have 4 cutting edges, because to concentrate cutting forces into different directions, to have ability for this drill to be self-centered during the drilling process. And here you can see also the coolant channels, one coolant channel and the second coolant channel. Sometimes you can see the other channels, but it's technical channels for producing a hole for the clamping fluids. So both inserts can be clamped by screws. Inserts there can be more inserts on the one side of the drill and another side on the drill, but you'll see them only if you use a special drilling with bigger diameters. For example, 80 millimeters, 90 millimeters, and so on. It's possible to put here another insert, but on another level a little bit on these tools, and here, and so on. And the chip flute, you can see the different angles of the chip flute. At the beginning, it's a little bit steep, then more aggressive, then again steep, and it allows chips to be evacuated faster to the beginning of the chip flute, and then with normal speed to be evacuated till the end, so till the end of the chip flute's exits. So shortly, it's also showed here on this slide, so you can see it in the recording, maybe even better on a presentation if you would like to read it after. For sure, we named our drills special way, but it's very easy to understand what doesn't mean. For example, here it doesn't mean that it's a series of the drill with a diameter of 15.0 millimeters. This is the right version with right-hand version with 4 diameters lengths, with side lock clamping and with a shank at 25 millimeters, symmetric, and it's for insert size number B, if I can put it so. So depending on the diameter, indexable drills can use inserts for sure with different sizes too. Not only drill body change, but also inserts size. And as I mentioned, also indexable drills can be different, completely different, and differ a lot from what we showed now. For example, with another shape of the inserts, with a special central drill bit, or with I don't know, with completely longer versions. Also, gun drills can be with indexable inserts. And trepanning drills can be with indexable inserts, and so on and so on and so on. But today we will cover more the base, the most common design of indexable drills with the 2 inserts. One is peripheral, one is the central insert. So they are overlapping a little bit, and they're covering the whole radius in order to allow the drill to remove the material from the whole diameter as a result. So let's start to comment with 2 advantages to the main result of this webinar for today. Let's look at the diameter range. If we want to choose solid carbide drill, so you see that because of the production of expenses of cost of production of this drill, we can choose them only from very small diameters, for example, below 1 millimeter till 25 millimeter, not more. Okay, technically it's possible, but this drill will be super expensive because it consists of carbide everywhere. Shank is from carbide, flutes from carbide, and so on. So because of that, for bigger diameters, we are choosing the another types of drills or modular drills, so with exchangeable heads, or drills with indexable inserts. And in some areas, you can see some areas also are overlapping. And for example, diameter 20 millimeter, what drill to choose? Solid carbide, modular, or indexable? One of the parameters you can use for that is price, because less carbide is in use, more economical the drill or the tool. So it's the first advantage of indexable drill, because if you calculate the cost per tool, it's the first, how to say it, at the first parcel when you got the tool, but more important to compare after the first inserts or first edges are worn and you need to change them, because in indexable drilling you need to change only the edge, and after that the insert. In a solid carbide drill you need to change the whole drill, so yeah, it's maybe too long one, but anyway. And it's very expensive to change the whole drill. And the edge, if to talk about the tool life, the edge is only one here, because yeah, it cannot be indexed. So we need to change the whole tool. Another advantage of indexable drills versus other ones, it's a diameter range. So basically, you can see that we are using indexable drills from 12 millimeters to 68. If you talk about standard assortment, if you talk about specials, it can be much bigger, and then can be a little bit smaller. Yeah, in the depth of cut, depth of holes, we don't have such wide range of length of the drill. But it's only concerning standard assortment, because as a specials, we can produce it from 8 diameters to more and more. But the design of the drill will be changed sometimes completely, because we need some another carbide elements inside, which will guide, which will play the role of the margin. Because why? Solid carbide drill can be produced easily and used in deep hole drilling easily, because it's carbide, it's very rigid, and because it has two, or in such a long variants, it has 4 margins. So that's why they are helping to wide drill to the hole and not move from the edges, from the desired position of the drill. We want to get hole from that. So this is advantage number 2, bigger diameters for sure, and in general very wide diameter range, very universal drill because of that. Another fact, let's look a little bit closer to the design, to the inserts at first. You can see here the peripheral insert and the central insert. And when you calculate the cutting data, when you take the catalog or electronic catalog and choose the cutting speed for the for drill is been chosen for this point, for the maximum diameter, and maximum diameter is there, so on the peripheral insert. So for example, 150 meters per minute we chose, but less the diameter, less the cutting speed. Unfortunately, we cannot variate number of revolution every time, so it's constant. That's why near the center we have cutting speed about 0 or 20% or 50% in different points of the diameter of the drill. That's why it's better to use different grades, different carbides on different diameters. And if with indexable drills, it's easier to do this. With solid carbide, it's almost impossible. There are technologies of sintering of different substrates on different levels of solid carbide, but generally it's specific tools, and they are even more expensive than usual solid carbide drills. Here we can choose just another carbide for the periphery insert, and that's in most of cases what we are doing. So we are choosing the toughest, the softest grade, which can resist to shocks, to hits, and to push. So because here, when the cutting speed is about 0, cutting edge is not really cutting; it's more pushing the material, not cutting, because that very low temperature and very low is almost 0 cutting speed. But on the periphery inserts, the cutting speed is maximum, and a lot of temperature is there if we work in productive way with higher cutting data. Here we can choose very simply the grade which is harder than the grade for the central insert, and as a result, we are increasing the cutting speed. Or if we don't want to do this, we want to increase to make the tool life longer. Then, if we would use a modular drill or solid carbide drill, there we cannot. We are using the central insert grade for the whole diameter, unfortunately. So this is a disadvantage of solid tools and modular tools, and the good advantage of indexable ones. So advantage number 3: different grades for tool life increase, or for different inserts. If we look at the inserts, also what help us to prolong the tool life, it's more advanced geometry of the insert. You can see here it's not straight; it's more complicated. In order to allow us to, during the coming to the material, to do this gradually, not immediately in contact for full diameter. So at first, the contact start with the central insert corner, if I can put it so, then again is another points, and then peripheral insert is starting to be in cutting action, and so on. So it allows us to not have any chippings during the entrance to the material. And here you can see on this slide how they are complement each other, so overlap the whole diameter and radius. Also, you can see the insert shapes, they are slightly different, not only because of cutting behavior, but also because to avoid mix inserts for the operator. So operator can, if the shape could be the same for the peripheral and central, operator could put central grade, the soft grade, very tough, but not strong, not hard at all, to the periphery place, to the periphery pocket. Thus, it will bring him to the much faster flank wear. Vice versa, if he wants, or he or she want to put a peripheral insert on the central place, hard peripheral insert on the central place, they can get a cracking or breakaging of the central insert. In order to avoid that, to use the maximum cutting conditions with the maximum productivity, shapes should be different, and it's not possible or very hard to put peripheral insert on central and central on peripheral pocket because of the grades. And together, these inserts also designed to self-centralize drill during the cutting action. So it's maybe the biggest advantage in cutting action of indexable drills versus other ones, because this drill can enter to a regular material, unstable surface, cast surface, and so on, without any pre-drilling operations or pre-milling operations. And this is advantage number 4. No problem to enter to any shape of the surface without any additional operations before the drilling. What I mean in most of cases, irregular surfaces, like here, for example, it can enter to inclined surface, it can enter to angle surface, it can enter to half diameter surface, so partially cut the diameter, to cylindrical surface, to make a chain drilling, to have a cylindrical or cross hole drillings, and so on and so on. And some of the operators, for example, this chain hole drilling is helping us with milling operations. Because, for example, with pocketing, sometimes we need to consider depth of the pocket. And if it's too big, maybe it's faster to use drills at first and to plunge, to remove, not always the plunge, but to remove materials by drillings. And then finally to have a finishing operation by milling cutter, for example, solid carbide or indexable milling cutter, doesn't matter, it depends on the component. Also possible to do helical interpolation by indexable drills, but it's an additional feature. So let's look at some of these features in action in at the following videos will be shown to your screens, on your screens. Now there should be another window appearing on your screens, and you will see. A second. The video. At this trial, you can see that we are machining the steel cube, and everything is ideal, almost ideal. The only not ideal that we are not using coolant here. So basically, in all of cases of drilling operations, we recommend to use internal coolant, or sometimes external, but also it's not good to do. Next, it's a much more demanding application. So we are going through the another hole, crossing the hole on 90 degrees with the angle 90 degrees. Usually, it is possible to do by any indexable drill, but we need to decrease the feed about from 30% to 3 times. Here you can see we are not decreasing the feed, so it depends on the design of the drill. For some, in general advice to decrease the feed in the cross-hole section, but not every time. Another application, entrance to the angle socket. Application, but anyway, it's also a little bit complicated. It's the exit to the inclined surface. Much more interesting application is the entrance and the exits to the angled surface. So basically, because of the insert design, it's not complete. It's different much from the solid carbide top design. So here we have 2 cutting edges. They're beside the conical. We have double angle and solid carbide drills, and also tip drills, and also drills with modular heads. They need this center part a lot. So if center part of the solid carbide drills is not in cutting, it's decentralize the drill and it can be broken. Here, this drill, indexable drill with those cutting edges, so you can see the start of the cutting. Maybe you'll see in this camera. Is starting to work not in the center, so a little bit from side from the center. It's much more stable. plunging operation by the drills, but deep plunging. And now entrance to the cylindrical surface, and for this surface or the axis of the drill is moved a little bit from the axis of the cylinder. So it makes usually it should cause a lot of vibrations and very poor surface finish, but not in this case with indexable drill. In some cases, you can use indexable drills also for stack materials drilling. So when one component is laid on another component, but they need to be clamped in very rigid way, like here, they almost can be said they are braced, and the gap between them should not exceed about 1.5 millimeters, because when you use indexable drill, there are small or narrow disc is been going out from the first component to the second, so in the space of this gap, and it can destroy the insert. So basically, if the gap is very small, there is not a problem to do that. But in general, for the stack materials, we recommend to use modular drills, not the indexable drills, or to use special indexable drills with another inclination, with another combination inclination of inserts and tire gauges. The question was about the feed. Yes, it was approximately the same, but we recommend in unstable, especially in unstable surface machining, to decrease feed about 2 times. Or you can try with a normal feed at first. But if there are problems, for example, after some time there can be cracking of the central insert. One of the way to avoid this is to decrease the feed, so you can start fighting with a problem when the problem appears, because it may not appear. So maybe there will be no any problems. But if there are, decrease the feed, and in future with machining of this hole, decrease the feed. For sure, in general, recommendation is decrease the feed on the entrance at first. And for sure, in unstable elements. So, for example, cross-hole drilling. So, when you cross the hole, when you drill, so here, there, about 30% to 2 times better to decrease the feed. Because this webinar is dedicated not only to our drill named Top Cut 4, but basically about all drills, indexable drills. And we're not sure what other drills may do better or maybe may do worse from another producers. So it's like general recommendation, decrease feed about 2 times. In some times when a producer is recommending to not decrease feed much, not decrease, only decrease if there are some problems appear, small problems. So next advantage, so there was one of the advantages, very good universal use in different applications and very good rigidity and very good working in unstable conditions. Here, another very nice advantage is you can use this, the same drill for machining of another diameter, hole with a bigger diameter or even with a smaller diameter. A lot of drills, the center insert, now I hope you see the presentation. Center insert is crossing the center, so a little bit, and there is a small, again, gap, and you can move a little bit to the left this drill on X, to the direction of X axis, a little bit, because about 0.1 or 0.2, and machine the diameter, for example, 19.8 or 9.7, 9.9 by using the drill with the diameter 20. But in most of cases, we want to increase diameter a little bit. So, for example, from 0.4 to 1 millimeter on radius, on the diameter, it will be 2 times more. So up to 2 millimeters, a bigger diameter we can machine, moving the drill axis from the rotation axis. How to do that? In milling machine tools, we can use a special chuck, drilling chuck, which has eccentric mechanism inside, and it can a little bit move the drill inside to periphery insert or to direction of central insert, and that way we can produce the hole with a little bit another diameter than the diameter of the drill. Another way to do that is to much easier when we use rotation of the component inside the turning machine tool. So we can move just the tool, like a turning tool, to periphery insert or from periphery insert, and we can get the hole bigger or larger or smaller. Generally, it's recommended, like for turning tools, if we talk about turning, but not only these manipulations. When we use, when we need to produce a drill up to 4 diameters, with a longer version of the drill, 5 diameters, or for example 6 diameters, it will be a little bit complicated. Vibrations can appear with such moved position of the drill from the axis. So it's advantage number 5, different diameters by one tool. Next advantage is similar to previous, so it's like a result of the previous. So by moving the axis to plus or to minus, we can adjust tolerance of the hole. So basically, you know that indexable drills producing the holes not super precisely. So it's maybe one of the disadvantages of this tool. From allowance 11 or 10 to allowance 14. In order to be close to the tight tolerance, we can use this such kind of chuck, eccentric chuck, or eccentric sleeve also. I did forgot to mention eccentric sleeve to use with the standard chuck, which can move the center of the drill out of the center of the rotation of the chuck, and that way we can produce a hole closer to what we need from the drawing of the component. And also another result of this moving or shifting the axis is we can use the tool as a turning tool. So basically we can use this tool, be more precise, periphery insert of the tool, like a turning tool, like a tool for internal turning. So just moving to up and turn, machine and machine, a hole to make a larger hole, much larger diameter of the hole than the diameter of the insert. And another sub-advantage of this advantage number 7 is to not wasting time. So sometimes you need the time to exchange the tool. Here you do not need to exchange. You drilled the first hole, and then you have this like boring the internal turning operations. So yes, it's like rushing turning, but anyway, you will get the size you need, and then you can use the finishing tool to get the final tolerances and sizes of the hole. And sometimes in the turrets you have a lot of tools in the turning machines, and you don't have space for extra turning tools. Sometimes it's enough to have only one drill. For sure, to get the best tool life and cutting data, better use turning tool for internal turning operations. But sometimes there are compromises, and you need to use what you have or what you don't have. If you don't have space for the turning tool now, so you can use drill. So how it can be performed, let's look at the next video. You could hear some noise, but it's very, very normal noise, I can put it so. Noise is not normal when it is irregular, when sometimes it's have one sound, then another sound, then no sound, and again sound. That means there's something strange with the chip formation. Here, it's a very, very normal process like we can see now. So we produce the hole at first shot, first pass, and then we are moving the drill to the direction of periphery insert, and then making the internal turning operations. Shorter the tool, better results for in internal turning, and the chamfering in the end. So, like, you can produce a conical holes as a result of, because you have in most of cases CNC turning machine tool, and you can program just moving to make a chamfer or conical hole. Also, you can use the drill also for milling, but it's not recommended, only in the critical situations, if you don't have end mills or another milling cutters at all. Another advantage, we can place a lot of different grades and chip breaking geometries to the periphery pocket and to the central pocket. This allows us to use the same tool body on different materials. So on steel, on cast iron, stainless steel, aluminum, and also some hardened materials. We will see the video now. So here you can see we have 5 different geometries. One is universal, by the way, it's a new product 2022 from Vidya. And also another ones are specials. For example, V36 is a stronger geometry for steel and cast iron. V36 sharper geometry for stainless steels and low carbon steels, and also super alloys. V36 for aluminum is even more sharper than usual V36, and we using it for aluminum drilling. V38 is a chip breaking optimizer, so the sharpest cutting edge among all of them, and we are using this geometry for long chip for long chipping materials, low and very sticky stainless, low carbon steels and stainless steels. And also different grades, different carbide grades, from the toughest one, that, for example, W40PH till WPK10CH with CVD coating for cast iron, and one of the also coating grade for aluminum, WN10PH. Combination of different inserts, different grades, and different chip breaking allow us to be more flexible and to be more universal in use. And let's look on some in other videos when we will machine Hardox material. but it will be plunging operation. So this videos will be from workshops. Thank you very much who's sending to us different videos recorded by the phone. So some of them we are using in webinars like now. Another operations will be aluminum drilling, and another operation will be drilling and the turning and of steel. Workpiece material is the Hardox 500, and the feed is 0.80 millimeter per tooth. It's not showed here in the video. I remember also cutting speed is a little bit more than 100 meters per minute. Aluminum drilling. Aluminum alloy 7075 to be. So very, very fast. So cutting speed more than 400 meters per minute. And you can see also other parameters now on the screen. After first staging and longitudinal turning. So now the drilling, and then there will be internal turning. So main cutting data. So we watched several different videos how to choose the cutting data. I hope most of you know. Basically, we are using catalogs. We are using electronic catalogs, and what is written showed here with green color. So this main parameter we take from the catalog. So cutting speed or velocity of cutting, and also feed per revolution or feed per tooth. But for indexable drill, it's the same. So because the tooth is only one, we can recalculate cutting speed to spindle frequency or revolutions per minute by usual formula, depending on the diameter of the drill. Multiplying this number of revolutions on feed, we can calculate the speed of feed or penetration speed VF in millimeters per minute. When we know that and know the length or the depth of the hole, we can easily calculate machining time. So dividing one by another. Okay, we need to add some more length, some more millimeters, for example, because we need to come up to the hole and then start to drilling. So there's some space, some gaps before and after, and we need to evacuate drill from the hole after. So it also takes time. But the main machining time can be calculated on this formula. And one of the main parameters of the every tool is the machining removal rate. So Q is a multiplying of penetration rate. So the rate we are going down or going up, so going into the hole, multiplied by the area of the circle. So which depends on the diameter of this hole. So multiplying them, we can calculate the metal removal rates in cubic centimeters per minute. About the cutting speed here, I just indicated one more time that we are choosing cutting speed for the peripheral insert, for this dot, for this part of the insert. Here, and here, it will be much lower. Here, for example, the catalog data, according to the material, P1, P2, P3, and so on, we are choosing the feed, and additional parameters are for sure diameter. Here you can see the range of diameters. Bigger insert, a little bit stronger the cutting edge. So the feed is bigger. And also you can see the first choice of grade and geometry for this material, for this condition, stable, unstable, and super unstable, interrupted cut. So you can you can see that if a little bit unstable conditions, like a chain drilling, wholesale drilling, you need to decrease the feed, but yeah, here it's almost invisible. Sometimes invisible when materials are more challenging. And you can see that this chart is related to short types of drills, if I can put it so short, 2 diameters and 3 diameters. I don't mean 1 diameter. For 4 diameters, 5 diameters length of the drill, there are similar charts here. So these charts are including almost all conditions we can face with. Conditions, diameters, and also length of the drill, depth of the hole. The same is for cutting speed. You can see also depending on the cutting conditions and the diameter and the material, sub-material group, we can choose the starting of cutting speed value, and we can increase it and decrease depending on the results of the first cuts. Also, we need to understand what coolant we will be using. It's mandatory to use the coolant, especially internal coolant. And the volume of the coolant per minute should be, yeah, better for sure. But approximately it's equals to the diameter of the drill. For example, 20 millimeter diameter, 20 liters per minute should be the coolant flow to the coolant channels. But here it's a little bit more precise graph. Here the minimum line related to minimum volume and to maximum volume of coolant. In order to evacuate chips, pressure is not that critical for indexable drilling like for solid carbide drills. But anyway, smaller diameter, it's more important to choose normal pressure of the coolant. Bigger diameters, bigger holes of the coolant channels. So not so big pressure is needed for bigger diameters. And the lengths, if we're using the longer versions, 5D, 4D, pressure higher and higher are required. And this is a minimum. So here's only the border of minimum pressure. So better to use more, 2 times more pressure, for example, up to 70 bars. We can use MQL, but basically we are using them more for aluminum drilling. Cutting oil or cutting media should be with concentration from 5 to 50, usually 6 or 7% of coolant mixture. Dry drilling is not recommended, but it's better, drill better survive in horizontal machines than dry drilling. And better to use them on short, cheap materials. For example, cast iron. So how to control the coolant flow? It's easier. You need to have the can, for example, 10-liter can, and turn on the coolant and to calculate the time when it will be full. So it will be 10 liters per, for example, minute. And you can compare if it's enough or not, or you can ask operator to increase the the volume, the coolant. Power and torque. So depending on the material and the diameter, it's very required to at least to start to think about it before the drill start to cut. But better to use our electronic catalog, Vidya Novo, which is based on the www.vidya.com and calculated there. So I came to the end almost, and here in the end, I want to ask you the question. We have two types of drills, modular and indexable, for the same diameter with the same depth. Which drill will be the most effective from your point of view? The same material, the same diameter, the same length. Which drill you would use for such kind of machining, modular or indexable? Poll will now appear on your screen. And I will show the answer after. Yeah, so now the topic is indexable. It doesn't matter that it will be the best one in this case. This question is a little bit tricky because effective, it's not precise meaning what I mean in effective. So yeah, about 43 for modular, 43% for indexable, and the rest 7 and 7. The same effectiveness, I'm not sure. Okay, now, yeah, I see that modular, there are more fans of modular drills. So previous webinars by our colleagues, which video was showed, they were very popular, as I see. Okay, let's close the poll and show the result. The winner from the votes is modular drill. Let's look on it a little bit deeper because effectiveness can have two meanings. Okay, now I hope you see now the presentation again. If we calculate the cutting data, I showed it how to do that. You can see that we have penetration rate about 400 millimeters per minute when we use standard indexable drill with standard cutting data for the steel. You can see here the feed is not so big because tooth is only one, but higher speeds because here the periphery insert with harder grade than the grade of usual solid or modular drill. Here the cutting speed is lower, but much higher feed because there are two teeth. And also the solid is most stronger usually than indexable that consists of different cutting elements. That's why feed is more than 2 times greater than feed for indexable drills, and penetration is almost more than 2 times greater. And in average, time of one hole with modular is 5 seconds. Times for one hole or for machining of 60 millimeters by indexable drill is 10 seconds, 2 times more. You can say, oh, it's not effective. In productivity, you are correct. Machine time shortage by 2 times. It's very nice. But if you will calculate the cost per part, and what does it mean? I will try to show now in another document very shortly. 1 second. Yeah. Some of you may remember we had a webinar about economics when we calculated live what is cheaper, what is more expensive, how to calculate machine tool rate. So average machine tool rate, if it costs 300,000 euros, is about 50 euro. Depends on the salary also of the personnel. Cutting tool cost, if we open the price list, we can see, for example, here the tool body price is approximately the same. Number of instances even more for indexable drill than for modular drill. Yeah, you're right here. But price per head, because volume of the head, size of the head, it contains much more carbide inside, is much bigger. than a price for two indexable inserts. And even more critical, that inserts smaller and cheaper because of the volume, they have 4 conic edges, not one. And you can see the tool cost per one tool life period is here the about 150 euros. Here 14 euros. Also, you can say it depends on the tool life of the body. Yes, it can be different. You can increase here to 100 too. Yeah, it's decreased, but not that much. And this tool cost sometimes it can influence on the minimum, on the getting the minimal cost per part. Not in this case. Here, for example, we put in the tool life. Okay, we need to test for sure the tool life, but here you can see that I put even almost 2 times more tool life per edge for modular drill than for indexable drill. So a lot of advantages of tool life here you can see, but because of the lot of cutting edges, because of the very low price per insert, we can see that per one component we have the cost per part below 3 euros for Top Cut 4 and for 50 holes, like in the task in the slide. And for modular drill is a little bit more than 3 euros. If you multiply by the batch, what was also on the slide, you will see that we will save 100 euro per batch. We use the indexable drill versus modular. It doesn't mean the modular drill is super expensive and we will not use it. There is a lot of ways when we need to use modular drills. For example, when we have only one machine tool and a lot of components. So when we need to produce a lot of holes per minute and we don't have any capacity, we need to move to produce it fast. So we cannot make it with indexable drills only with one tools. We need to use it. We need to use more productive tools like a modular. But if we calculate the cost per part, it's about 15% in this case, lower cost per part for indexable drill. So it's advantage number 9, lower cost per part in a lot of cases when you use indexable drill. So we are out of time. I will just show it. You can make screenshots if you want. So how to solve the problems we can appear with usage of different drills, but here in particular when you use indexable drills. And one of the questions also I see on the chart, can we mix the different geometries on different places? So a peripheral pocket and central pocket. I can answer yes, but it's not mandatory. So you can choose, for example, periphery geometry, stronger one, when, for example, you are facing with when hole diameter is larger than diameter of the drill. So if it's larger, it's the sense of it, or it can be as a result of deviation of the drill inside the hole. That's why it's larger. So in order to avoid that, you can clamp the stronger geometry to the periphery in order to allow drill a little bit more being centralized. So it's peripheral instance will centralize better the drill inside the hole. And also diameter is smaller than diameter of the drill. You can make the vice versa way, so to change it to sharper geometry. And also other tips and solutions to the possible problems you can face with because of the chip control, because of the not correct feed, because of different areas, and also other where you can face with, like in turning, for example, you can face with plastic deformation and build-up edge. In order to avoid those, I don't have a place on this slide and time on this presentation to show it, because this way is common, and you can watch again the webinar which were in the middle of the previous year, named "How to beat with wear," how to fight with wear. So you can use solutions from there, but more related to the indexable drills showed here, so which are more connected to the hole quality and central and peripheral inserts in particular. So what to choose? Each kind of drill has its advantages. Solid carbide, the best for small diameters and not so expensive. The highest productivity, also high feed because usually 2 teeth on it, and as a result, bigger, higher metal removal rate. Modular, the same, but tolerance not so good, but also normal for intermediate diameters. Indexable, and for mass production, with fast production, when we need to produce a lot of holes and you don't have a rest capacity to have more machines, so you can optimize the machine using modular drills. Indexable drills, low cutting tool expenses. Longer tool life if speed is not so high, but you can higher speed for sure. Very wide diameter range and very big diameters possible. Better for unstable conditions, and managing in most of cases with delivering the lowest cost per component, cost per hole. So here I'm finished the presentation. Thank you very much, and I'm ready for the questions.
Vladimir, we have a few questions here. The first one is, what is the best indexable insert option for drilling Asteloy X for 15 millimeter diameter at 4 times D?
Yeah, thank you for the question. So let me come deeper to the material properties. So it should be, if I'm not mistaken, one of the type of the superalloys, probably S2. So if yes, so I need to double check it. You need to use grade WP40PH for the central insert and the same for the peripheral insert. So it's the first choice for superalloys for us. The geometry, if there are no any additional requirement to power, I mean, if a machine tool is not weak, so 36, geometry 36 should be enough. So geometry 36 and the WP40 to the periphery and to the center. If I will find something abnormal in this properties of this material, Asteloy X, so I will contact you directly and answer in email.
Okay, perfect. Thank you. And is it okay, Vladimir, to use indexable drills for dry cutting or without coolant?
Basically, yes, but it's more or less reliable when the depth of the hole is not exceeding 1 diameter. Possible to use up to C diameters, but usually only on horizontal machines it's better, because you need to try, but better to try with coolant to avoid dry cutting. If to dry cutting, I would check on different depths. For example, you need to cut 3 times D. Try to go on 1 diameter. Look if everything is okay, no chip jamming, no any strange sounds. Go to 2D and then to 3D. Then increase the length of all passes, and then increase to final pass. I mean, to check the reliability of chip evacuation process, because usually if the tool is assembled with carbide and steel, so combination of carbide and steel, it's more critical to work with a coolant, because it's also critical. It also can be overheating inside. If you, for example, machining 4 diameters, there can be overheating of the top, and it's critical for the steel part of all tool bodies drills, if I can say so. So you can check, but better recommendation to avoid dry cutting, or if to do that, only on 1 diameter or on horizontal machines, and better to work with short chip materials.
Okay, and before reading the last question, I wanted to remind the participants that tomorrow you will receive the recording of the webinar. So don't worry, I know it's a lot of information, but you can listen to it again. Actually, this is not a question, Vladimir. It's connected to what you were saying before about the economics of metal cutting. This person says, if the hole size is critical, I choose modular. If the cost is critical, I choose indexable.
Yeah, very correct answers. Thank you very much. Yeah, because we didn't talk a lot about tolerances today. We just mentioned it, but for sure, modular and solid is much more precise. And also, we didn't cover the chip control with which type of chip can be produced by central inserts. In the beginning, it's like Christmas tree, but should be middle segmented. And from periphery, it's like from turning inserts, should be not a problem. I don't have slide here, don't have time to touch this, but it's maybe second topic I will touch more detail maybe next time.
We don't have any more questions for the moment, but I think, Vladimir, if there are any more, please just answer to the follow-up email that you will receive and we will get back to you. And thank you very much for being here today. I know it's a little over time, but Vladimir, I think it was worth it because you added a lot of useful information. So we hope to see you in the next webinar. Thank you, Vladimir, for presenting this. And
on
let
this
us know
slide, you can find indexable drills in this QR code. It's leading to our website catalog. If you need to choose it now, you can go to video.com or scan the QR code. It will lead to it immediately. It's just a result of the webinar. Start to use indexable drills if you didn't use before, and don't afraid to do it. And it's maybe the most reliable drill we are working with, especially for non-stable conditions. Sorry, I interrupted you, Isabel.
No problem. We will leave a few seconds so you can catch the QR code. Okay, perfect. So thank you very much, and we will see you in the next training, and have a great rest of the day.
Thank you very much. Have a good evening. Thank you.